This is GCSE Further Maths. We're looking at the Unit 2 Mechanics paper, and this is from 2019. So let's take a look at the question. First of all, define a vector quantity and include an example in your answer. So what they want to know is that you know that a vector has magnitude and direction. So plenty of different examples you could use for that. Velocity would be fine. Displacement, force, acceleration, something like that. Define a scalar quantity, exclude an example in your answer. A scalar has magnitude only. An example, I guess a good counterexample then for the velocity would be speed. Or if you wanted time, or something along those lines. Question 2. A body is initially at an origin O and travelling with an initial velocity of minus 3i plus 2j. It moves with a constant acceleration of 4i minus 6j for 4 seconds. Calculate the displacement of the body in vector form after 4 seconds. So we would use UVAST. Initial velocity is minus 3i plus 2j. Our acceleration is 4i minus 6j. Our time is 4 seconds, and they want to know where it is, so that then would be our displacement. So we would use S equals ut plus a half at squared. S equals, so it's going to be 4, this here upon this, so u times t, so it's going to be 4 upon minus 3i plus 2j plus a half, and then my acceleration is 4i minus 6j, and then my t squared is going to be 4 squared. So we are going to have, let me see, timesing this through then by 4 is minus 12i plus 8j. And what about times this through? That's a 4 squared, so that's a 16, and then half of that. So I'm just going to times through this one then by 8. So it's going to be 32i minus 48j. Joining together the I terms then, so minus 12 plus a 32 is of course then going to be 20. And then 8 minus 48 is then minus 40j. Sorry, you can't see that at the bottom. 20i minus 40j. The speed of the body after 4 seconds, and note of underlined speed. So we're going to work out velocity. That will be in a vector form. And then we'll do Pythagoras to work out what we have. So we're going to use v equals u plus at. I bring the previous page back, you can see the information then that we have. So we're going to have v is the u minus 3i plus 2j plus 4 upon 4i minus 6j. So my velocity then is going to be, that's going to be 16, take away 3, so that's 13i, and then it's going to be minus 24 plus 2, so minus 22j. And so my speed then is going to be the square root of 13 squared plus minus 22 squared. And so if you square this and square this, put in your calculator, find the square root, we get 25.55. So 25.55 meters per second. Find the angle the velocity makes with the positive x-axis after the 4 seconds. So after the 4 seconds, we're 13I minus 22j. So how does that look? There's 13, and then there's your minus 22. And we're asked to find the angle, so we can see I is the same as n as the x-axis, as we're saying, the positive x-axis. So we're looking for this angle here. If I call that theta. That's the opposite. That's the adjacent. So we're going to be using tan. Tan theta is O over A, so it's 22 over 13. Theta is tan to the minus 1. 22 over 13. Again, just plug it into your calculator and you will get, let's see, move this down a bit first, 59.42 degrees. Let's take a wee look then at question 3. A block of mass 5.8 kilograms is initially at rest on a smooth horizontal table. The block is then pulled along the table with a string of force 17 newtons. The string makes an angle of 33 degrees to the horizontal as shown in the diagram below. Mark on the diagram above the other forces acting on the block. So there's a 5.8 G that acts down like that, so it's going to be 5.8 times 10 if we need to work it out. And there's a normal reaction acting up like that. We normally call that R. Sometimes there'll be a friction here, but it says it's a smooth table, so there's no frictional force then acting like that. Calculate the normal reaction between the block and the table. Now, quite often it's nice and straightforward, because so first of all we're in equilibrium, so it's everything going up equals everything going down, and quite often it's R equals 5.8 G, but this 17 comes into effect. If the 17 was acting this way, just horizontally, then it wouldn't have any effect, but it does here, so we just need to be careful with that. So we're going to resolve vertically, and resolving vertically we're going to have R plus 17. So let's see what we're doing. The 17, and it's going that way, so we're not going across the angle, so it's going to be sine. So 17 sine 33 is equal to 58. That's my 5.8 times the 10. Rearrange that. 58 take away the 17 sine 33, and I get 48.74 newtons. Calculate the acceleration of the block. So because it's been pulled along here, then there's going to be an acceleration going this way here. So we're going to resolve horizontally using F equals ma. So F equals ma. I quite often do the right hand side first because it makes it more straightforward. The mass is 5.8 and A is what we're trying to work out, so that's going to be 5.8 A. And then let's see what forces we have acting in the direction of the acceleration. So we have the 17, and we're resolving it this way here. So notice I went across that 33, so it's going to be 17 cos 33. So 17 cos 33 is 5.8a. And you put in your calculator to get A is 2.458. We need to give answers to 2 decimal places, so it's going to be 2.46, and the unit's already in there for us. Find the speed of the block after 5 seconds. We're going to use UVAST for that. U, V, A, S, and T. U is 0. V is what we're trying to find out. The acceleration we've just worked out. Now remember, use the more accurate version. 2.458 or whatever number you have in your calculator is better than that, and it's after 5 seconds, so my time then is 5. V equals U plus AT. V equals 0 plus 2.458 upon 5 times by 5. Put in your calculator, you'll get V then as 12.29 meters per second. On then to question 4. A uniform rod has length 3.2 meters and mass 4.6 kilograms. It is suspended from a ceiling by two inextensible strings. Inextensible strings attached to points C and D. The distance AC is 0.6, the distance DB is 0.4 as shown. A mass of 6 kilograms is attached to the rod at the end A, and a mass of 8 is attached to the rod at the end B. The rod remains horizontal in equilibrium. Mark on the diagram all the forces acting on the rod. So a mass of 6 kilograms is attached at A, so that's going to be 6G acting down like that. At end B, there's an 8G. Don't forget, obviously the mass is 4.6 kilograms and acts down through the middle because it's a uniform rod, and that's 4.6G. And then there's 3 forces going down. So what are the 2 forces holding in place because it is in equilibrium? We're going to have here T1 and our T2. I'm going to fill in some distances here as well. It's 3.2 meters long. That means halfway is going to be 1.6, because remember this acts through the middle. So that then would be a 1. That might be of use to us at some stage. And this distance here, because if that's 1.6 as well, then that's going to be 1.2. That's not part of part 1, but it's just going to be useful then for the next wee bit. Calculate the tensions in the strings at C and D. So we want to take moments somewhere, and the most sensible place to take moments is here or here. So I'm going to take moments about here because that eliminates the T1, and we can work out then the rest from there. So make sure and let the examiner know where you're taking your moments. So I'm taking my moments about C, and for any moments the clockwise equal the anti-clockwise. There's a few forces here we need to deal with, so let's see if we can work out what's going on. Here's a rod here. I'm putting the pin in here effectively, so it rotates kind of around here. The 4.6, that's taking it clockwise. The 8, that's taking it clockwise. Pushing the direction of the T2, that's anti-clockwise. And there is another force, don't forget about it. That's 6G, that moves it anti-clockwise as well. So my 2 clockwise forces are 4.6 times by the distance, which is 1. So 1 times 4.6G. And then this distance here, which is going to be, is that going to be 2.4? 1 plus 1.2 plus 0.4, 2.6. Yeah, 2.6 of course. 2.6 times 8G. So let's get those written in. So I said that it's 1 times 4.6G plus 2.6 times 8G, and then the anti-clockwise ones, that distance there is 2.2 times T2 plus 0.6 times the 6G. Let's do some calculations. 1 times 46, 80 times 2.6. That's 208. 2.2 T2, and then 0.6 times 60 is going to be 36. So let's see then what we have here. So we have 2.2 T2, and then I'm going to do 46 plus 208, take away 36. That's 218. And T2 is 218 divided by 2.2 is 99.09. It's repeating, so that's it. So which one is that? That's the T2 I've worked out. That's the tension at D. So tension of the string at D is 99.09. How are we going to get the tension at A? We could take moments about the tension at C. We could take moments about here, that'll be fine, but that's harder work than we need. We know it's in equilibrium, so everything going up equals everything going down. So we're going to resolve vertically. So T1 plus T2 is equal to 60 plus 46 plus 80. That's just the 6G, the 4.6G. 80. And so that means then that T1 plus T2 is equal to 106 at 186. And then that means the T1 that we want is 186, take away our 99.09. And that gives us 86.91. That's the 2 decimal places. Okay. Question 5 then. A car of mass 850 kilograms tows a trailer of mass 350 kilograms along a straight horizontal road. The car and the trailer are connected by a light horizontal tow bar. The resistance to motion of the car is 1.2 newtons per kilogram, so it'll be 1.2 times 850. Resistance to motion of the trailer is 0.95 newtons per kilograms. The car and the trailer travel with a constant acceleration of 0.9. Calculate the tension in the tow bar. So I want all the forces we have acting on here. You have F here or E. I'm going to go for E for the force exerted then by the engine. We're going to have a T going here. We're going to have a T going here. We're also going to have a 1.2 times 850, which is 1020. And here we're going to have a 0.95 times 350, which is 332.5. So find the tension in the tow bar. We also are told the acceleration then is 0.9. That's meters per second squared. So if we do F equals ma, then for this, you can do it for this, you could do it for the car. The car will have two unknowns though, so it's a T and an E we don't know, so we're better doing it for this or for the whole journey. So I'm going to do for the 350 kilogram one, F equals ma. Right hand side first is going to be 350 times 0.9. And what forces do we have acting in this then? This is taking it forward and this is taking it backwards, so it's T minus 332.5. So that means T is going to be then 332.5 plus 350 times 0.9, I think that's 315, is it? And so my tension then is going to be 647.5 newtons. So I write it in here, 647.5. Part 2, the tractive force of the engine of the car. So we're going to do F equals ma again, only this time then for the car. Wonder could we see both here? Just about. Although I'll be covering it with my hand. Unfortunately, that's the other way around. It would make no sense, wouldn't it? So F equals ma, and that then is for the 850 kilogram car. So first of all, the right hand side, mass is 850 and acceleration is 0.9. And then what I've called this then is going to be E. Take away T, take away 1020. So this force is making it accelerate, this one and this one I guess are effectively making it slow down. We know the T, we've just worked it out previously, so our E then is going to be 850 times 0.9, which is 765, plus 647.5 plus 1020. Put that in your calculator. E is 2432.5 newtons. So just 7 in here, 2432.5. The trailer and the car and trailer started from rest. 8 seconds later, the tow bar brakes. Calculate the speed of the car when the tow bar brakes. So we're going to use UVAST for this. U, V, A, S, and T. Starts from rest, 0. V is what we want. Time is 8. And our acceleration, as we know, we've known all the way through, then is 0.9. So V equals U plus AT. V is 0 plus 0.9 times by 8. So V then is 7.2 meters per second. And again, sub it in down here. And we have that. Calculate the speed of the car 12 seconds after the tow bar brakes, given that the tractive force of the car and the resistance to the motion of the car remain unchanged. So once the tow bar breaks, things change, and it means then the tension is going to disappear because there's no tension from the tow bar. So we still have our E and we still have our 1020. So we need to find our new acceleration then from there. So here's my new car. That's 850. This force here is 2432.5. This force here is still 1020, and it's accelerating that way there. So we're going to do F equals ma. Right hand side is 850. A is a new thing we're trying to work out. And then 2432.5, take away 1020. 2432.5, take away 1020 equals 1412.5. That's 850A. So A then is this divided by 850. And that gives me 1.662. Do a few decimal places. So we need to find then, calculate the speed of the car after 12 seconds. So we're going to use UVAST here. U, V, A, S, and T. Now our U, hopefully you remember, is 7.2, because whenever the tow bar brakes, it's going at 7.2, worked out in the previous part. Alright. And we're trying to find the new speed, because it's going to speed up. My new acceleration is 1.662, and my time then is 12. So V equals U plus AT. V equals 7.2 plus 1.662. You can keep that number in your calculator, that's handier. Then times by 12. Put it into your calculator and you will get 27.14. And that then is meters per second. Question 6. Let's get rid of the other stuff here if we can. A block of mass 7 kilograms lies on a rough surface inclined at an angle of 27 degrees to the horizontal. The force due to friction is 18.7. Which of the following options would produce the greatest acceleration of the block? This one, the block is to slide down the slope, or the block is pulled up the slope with a force of 64.4 newtons. So we need to do F equals ma for both of these, and see which option then gives us the biggest acceleration. So first of all, the block is allowed to slide down the slope. If it's allowed to slide down the slope, then the friction will be acting this way here. So that's 18.7. We have a normal reaction going this way here, and then we have 7g acting down this way here. It accelerates this way, so we would do F equals ma. What force is making this slide down the plane? Well, it's got to be the 7g, so it's 7g and then sine slope, so 70 sine 27. Sorry for the noise there. 70 sine 27. Take away 18.7 is mass times acceleration, and it's 7a. 7a equals, so 70 sine 27. Take away 18.7. 13.0793. And then divide both sides by 7. 1.87. So that's that one. Let's look at the next one. The block is pulled up the slope with a force of 46.4 newtons. So what forces do we have acting here? The 7G still acts down. The normal reaction is still in place. And now the friction, remember, is going to go this way. So that's my 18.7. So F equals ma. Or sorry, we'll have a wee acceleration heading this way here. So we have 64.4. That's that force going that way. Take away 18.7. Take away 7. 7G is 70. Sine 27. Because that's me resolving this one down the slope. Equals 7a. So let's put that in our calculator. See what we have. 64.4. Take away 18.7. Take away 70 sine 27 equals, so 7a then equals 13.9207, and a then if I divide by 7 is 1.989. So the acceleration for this one is 1.989. The acceleration for this one is 1.87. So which of the following options produces the greatest acceleration? It's going to be then option B. So option B, and that's us done.